go live. Yeah. Docs. Chat. Hey, everyone. I think I'm live. My timing was a little off today. I have to run quickly and make a cup of tea, and then I'll be back. Cool. Need to go make a cup of tea, and then I'll be back. Yeah, man. Just hold on for me, and I should be able to be back shortly. Yep. On and on. Okay, cool. Everyone, so what do I want to do today? I want to try and I have an I2C application. Basically, I'm just trying to interface uh, a real-time timer, a real-time clock via I2C to my STM32F4 board. The reason I'm using an external I2C RTC module is because I want to be able to. So there's an internal RTC module, but I haven't done the necessary background work to hook up a VBAT signal onto my board. And due to that, I am I'd like to connect an external real-time clock, so that one that has a battery hookup. I have one here, one that has a battery hookup. And basically, what I want to do with that clock is to be able to just maintain a consistent time between boot sequences. Basically, the board can go out of power and into power as many times as possible, but I want to be able to maintain a clock, a real-time clock, so that just kind of defines what time it is now. Okay, cool. So, what's the situation we're in right now? We have an I2C. Maybe the title of this. What's this thing called? Maybe the title of this is called. Oh my god, that's stupid. Maybe the title of this is. Yeah. Sorry, I'm just a little bit frazzled because I'm making all my oh yeah, that's chill. Even if you saw that, you'd be okay. Okay, what do I want to do today? I have an I2C application. I was gonna call it a driver, but I wouldn't call it a driver. The reason being is the more you go into embedded development, especially more bare metal stuff, the more you gain a sudden realization, which is that you mostly write an application. You don't write drivers. How do I explain that? So, let's say you have a like the cover image of this live stream right now. It's an RTC module connected to a MCU via I2C. So let's say you have an application like that. You have an external I2C sensor, and you want to connect it to your onboard MCU. What you're going to do in this specific instance is you're going to develop a straight shot driver, if I might call it that. Yeah, there's a few ways of doing this. You can build a general I2C driver, and have it just sitting around in your code, and then that general I2C driver can be used to speak to this RTC module. So let's look at an example of that. Visual Studio. So let's get Visual Studio running, and then we'll look at an example of that. Perfect. I think this is actually the project where we're running it. So what you can opt to do is you can build an I2C driver that has like a few exposed application programming interfaces, API interfaces. And then once you have this driver, you can now use it to communicate with the device that you want to communicate with. In my respect, it would be tiny RTC module, which is based on a DS1307 real-time clock module. Details are unimportant at this point. Cool. So we have that. And the thing I was explaining before I kind of got tracked with all the module names is when you're building an embedded application, in the beginning you'll start out by, oh, I need to use GPIO. You'll find yourself building a full GPIO driver and then implementing whatever you wanted on top of GPIO. This is okay. This is reasonable. However, the more you develop, you'll realize quite a lot of that is wasted work. What do I mean? You can build a full GPIO driver that accounts for analog use, pull up, pull down, fast, slow GPIOs with high and low slew rates and all of those sorts of things. And then in the end, your application only has one vector or one way. Like you only use GPIO in one singular way. So is there really need for you to spend all this time to develop a very comprehensive GPIO driver when your application is only going to use two pins, and it's like, let's consider this example where our application is only going to use two pins, and it's only going to use those two pins in a certain way for I squared C. So we wouldn't need these two pins reconfigured for something else, or they will always be used for I squared C. So does it make sense to write a full GPIO driver, or can we do something like, as we can see here, just set up the two pins, which is a grand total of how many lines of code is that? This is from 65 to 81. So 81 minus 65, less than 20 lines of code. So 16 lines of code. In 16 lines of code, we can set up this I squared C pins, and we can use them as we need be, and our application is done. And we can, preferably, if we wanted to implement some test-driven development, it would be quite easy to test these 16 lines of code, and that they're doing the thing they're supposed to. So what am I explaining here? The farther you go into your embedded development career, the more you'll realize you don't really build drivers, you just build an application. They're easier to test as they've got a smaller footprint, you can get quicker with them, you can do it over and over again, it's easy to copy paste, you just be specific, handle this, what you're handling now, and be done with it. Don't build drivers for a future scenario. Don't improve on code you did 10 years ago because now it has to be fancier. No, just build what you need to build now, and move on. And this is actually quite how would I say it? Almost significant advice. If you're It doesn't just apply to embedded development. This also applies to like life and things like that. If you just deal with the present, then you leave possibility to tolerate the past and to handle the future when it does show up. Just deal with what is going on now and fix it, and improve it and go on with that. Just deal with that. Don't prematurely optimize for things that might happen in the future. A lot of time, a lot of energy goes through to efforts like that, and often we optimize for the wrong thing completely. Cool. Big long ramble. What does this have to do with I squared C? So I could develop a very general I squared C driver and then use that, but that's not what I want to do today. Or rather, that's not what I've done. I've developed a rather specific I squared C driver. You can use I squared C using blocking, which is you poll things, and then as you poll them, you can look at this. I have a repo that you can look at. But basically, you can have some sort of polling mechanism in your I squared C drivers, and then once you can basically use your, let's go to the source. I would say not that. Apologies. Okay, cool. So let's go to starting now. So what the way I'm using I squared C here is in a polling way. What does that mean? I enable my peripheral, I enable arcing, and then I send some data and I wait for something to happen, and then after something happens, if we go into this definition of master send data, we'll see that basically, yeah, I do something, I wait until a flag is set, then I do something else, then I wait until something else is set, and then I flag. So I want to avoid that, because the reason being, I want to get used to mostly doing all my stuff as non-blocking. So you just use interrupts, they're easy, they're nice. And given this, I have to develop a non-blocking driver, which I have. Okay, cool. Which I have, and is on here. However, my non-blocking driver does not do transceiver. How do you send? Well, transmits. it does not do transmits properly. Basically, what happens is whenever I transmit a number of bytes, the last byte is never arced. And this is most likely due to something I need to enable. That's deleted code. I've been reading a bit, and I have an idea. I think what I need to do is not mess with my arc bit. So I need to not disable my acknowledge, and I will get the last the last piece of data. So let me run a trace for you so that you see what I'm actually blocked at. And then once I run my trace for you, we can now jump into the code, and we can jump into the reference manual, and we can explore what's wrong with my code. So let's get pulse view running. And yeah, we do have an SCL and SDA, perfect. And then I want to do something like 10 million samples, but I want to do them at something like 250 kilohertz. We're running I2C on standard mode, SM. So we're running at 100 kilohertz. So I would just want to sample at a rate that will allow me to get all my bits. Okay, cool. Start debugging. So let's see. Cool. Okay, let's see. Can we debug here? GDB remote. So something's up. I just need to unplug and replug my stuff. If I do it nicely, it should be good. And I run. Start debugging. Okay, cool. So am I running anything else that is connecting to that device for speed? In terms to anything else? Pulse view, that's fine. OBS is fine. Discord is fine. Discord is fine. Okay, cool. So let's close that. Let's go here and let's go run, and then run without debugging. See if that runs. Why? So something is wrong. For some reason, okay, so stop. Okay, so if I use Cortex debug, something's broken in Cortex debug. So what's wrong here? What's wrong? Maybe I need to close pulse view. There shouldn't be anything else connected to this Cortex debug. I'm gonna quickly try a different device and then see if it's my device, if it's this particular device that's having a problem, and or this port. And then once we can figure that out, we'll go with it. Okay, cool. So let's try running. Ah, cool. Please not do the shit. What? Run? Okay, stop. Was I the one who was wrong? Because that just accepted and ran. So run. Okay. What is wrong? What has changed? My boot pins, there's no switch, no switch change. Nothing is really broken. So, okay, just okay, cool. So what's not working? Can I just run without debugging? I wonder if my jumpers have been messed up. Jumpers look okay. Jumpers look okay. Okay. Just disconnected everything from it. So, run without debugging. What is wrong? What is wrong? Okay, so I'll try that cable. This with this. Okay. Run. Okay. Okay. Run. Start debugging. Build connect. Okay. Let's remove that. I'm gonna be a little upset when we do find out it's a cable. But it's okay. Cancel. No, I'm not gonna update that right now. So start debugging. Disconnected. And you're telling me if I run with this, it will just work. this is the problem. Something's changed. I don't know what it is. Something has changed and I don't know what it is. So I'm not gonna give up. I think that's running. That is definitely not running. Okay. CMQ ID. Let's just go to blank Kimsys. I'm just gonna try and use STM ID and just see if I can run everything from a same place, and then blank F4. Does that toggle? That's all. Call source main. What do you do? Do you toggle? No. This is a bootloader. Should. Kimsys example. What does Kimsys example do? I just need some simple code to run, just so I can. No, this is not a Kimsys example. That's a very different. A 41. Yeah, I have this on the other side. It's the same code. Hello world. General timers. I'll probably run general timers and see what it is. General timers should give me a sort of a blink. So let's run that. Yeah, I'm getting blinks. And can I get blinks with the old cable? Old cable and the old board. Old cable and the old board. Just wanna see. So yep, old cable, old board, board's working, cable's working. Cool. So it's not the old cable, it's not the old board. Perfect. So now I go back. This is turned into some sort of Visual Studio debug session, I guess. Let's close that. Cool. So we know that works now. I'm gonna try and run general timers from here, just to see, start debugging. Run. Console. Run. Done without debugging. Okay. Okay, cool. So I'm just looking at this from here. Sorry. I'm trying to see what did I do wrong. Hey, look, it's the same board. It could be me. Okay. Okay, my general done. Let's close that. Close that. Okay, so it doesn't want me to have something where I was going. Cool. It's not good. What's the debug button? Don't. I did the BTM. I have a feeling this is auto-generated as well. Right. Start debugging. Codex viewer, can I do that? Are we running? Seems like we are running. Can I jump onto terminal? Can I look at that? And if I press that, do I see everything? Cool, perfect. We're running, so I have to just hook up my stuff again and go back to what it was. Okay, cool. So this is fine. We fixed that. That block we found is actually effective. You need to delete your build and debug folders. Cool. So now let's repower this thing and see what we can do. So number one, we want arc. We want so black is ground and white is black is ground. Black is ground and white is 5 volt. So let's put those in. Ground with 5 volts. Cool. White 5 volts. Ground is 5. Amazing. Sensors hooked up. Okay, cool. And then we want to do these pins now. What is it? PB6, port B, pin 6 is a CL. A CL. A CL is blue. Blue is white. Wait. SCL is blue. Blue is black. Blue comes through to black. So SCL is blue and that comes through to black, and SCL is 6. PV6. PV6. Yeah, eventually in the development cycle, when you have all of this done on one single PCB, life can be fun, because then you don't have to do all of this, but then you have to hook up your why do they sometimes it's so hard to use. Cool, I think that's okay. I think that should work. I'll run it one more time, and so we see some traces, yeah, just to make sure that everything is okay. I'll come here, and then I think we'll see some stuff. Yes, so we're handling the I2C driver is working okay, and it's running. Cool, so let's go back to our code. Now let's go back to pulse view. Okay. What I want us to see is a trace what I want to see is a trace of how the let's see, there any charts? No charts. That's not good. Cool. And the reason that's not good is because my pulse view is not connected, it's not hooked up. So let's hook it up. Amazing. Cool. So let's do pulse view. Get the things I want. Okay, cool. So now that's a problem. Anyways, 250 kilohertz, 10 amp samples. Let's run you, let's stop, let's run you, let's stop. The reason I do that is so I can move these guys down. Then this is D2, should be here. Okay. I'm gonna move this guy down. Come on, please. I usually am able to do that, so I'll just take D0 here and D1 here. That's fine for now. Cool, and then I'll enable D0 to be D0. D0 is the white one. SEL. Okay, and I'll label SDA. Okay, and then I'll add an I2C I2C decoder, and then here this should be SEL. Cool. So 10 million samples, 500 kilohertz. We can do 250 kilohertz, 10 million samples. Let's now run our code. Yeah. Okay, let's run it and see what we can get, isn't it? This should just set up all the pins and run that. I can stop it here because I don't need that anymore. Okay, cool. So I'm just gonna, we're ready to run. Cool. And then I'm gonna start recording here. Run, stop, run, stop. Okay. Run. And then I'm gonna go here and I'm going to run. And then I'm going back to my pulse view and I'm going to stop. And now I'm gonna zoom in. Ooh, something didn't go right. Run. Stop. They're both slow. Something is holding them low. Okay, so let's stop this. Let's run this. Start debug. With STM, WM. Okay. 250 kilohertz. 10 million samples. Run. Run. Okay. Stop. This is perfect. This is perfect. It's exactly what we wanted. So let's see. So oof. Now you can see my problem. So we send a write address. So we want to write to that address. We send address 68, and that's fine. And we get an arc. Okay. And then after that one, we send 2 bits of data. Here's where my issue occurs. We got an arc for the first one, you see. So if we send the first bit of data, which is the location to write, and then we send the second bit of data, and here goes. Here comes our first problem. We get a knock, and then because we get a knock, and we're done sending, we clear the knock. Our driver right now is clever enough to know that it's gotten a knock, and if it does get a knock, it should send a stop bit right after. Cool. Ideally here, we want to get, ideally here, if you know how better to use this thing so that I can zoom in and zoom out quickly, please let me know in the chat. Cool. What we want to get is a bit or a byte and then an arc after the byte. Okay? And when we get that arc, then we can proceed on to doing the BTF and the stop and everything. So what I have a feeling is that my application is not arcing the second bit. And if I recall correctly, when I was writing this code, I was kind of following the way I've done my blocking I2C code. So what I would have done is I would have handled that interrupt in such a way that let's just look at it. I think I handled the interrupt in such a way that stop all of that. We have a trace, and now my machine doesn't want. Why can't I open it? Why can't I open it? Why can't I open it? Okay, Visual Studio Code. Let's go in there, and let's try and open I2C. Okay, cool. So here's the thing. I think somewhere I'm disabling my arc when I don't need to. ACK 19, that's fine. Okay. Yeah, I see. I check for arc failures, and instead, if I get an arc failure, my callback will do basically what is okay. I think we are identifying one of our fast problems. So let's go here, manage arcing. I'm redoing a few things. So here I go arc pause and I enable arc. Okay, cool. So I know the first issue I'm doing is this. This is wrong. I don't need to do this here. I don't need to do that there. Because I don't need to do that there because I'm doing it extraneously. So because at the end of our initialize function, we enable arcing. Cool. So that's perfect. Can you find it before? Okay, can you find it below? Enable arcing. Cool. Amazing. I2C manage arcing. Cool. Okay, let me just go through this. I2C manage. Let's see how many places I've called this. Okay. 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 Close receive data. I'm not receiving data yet. Manage arcing. This is inside of init. Cool. Next one. Wait. So this is the first one. Manage arcing. This is inside of init. What's the next one? I2C manage arcing. That's fine. That's okay. That's just the function. I2C clear ADDR flag. I have a feeling. Let's see. Okay, that's the third one. What's the fourth one? Where are you? Handle RxNE. RxNE is not gonna be used when we're doing transmit. RxNE is never set. So this is not affecting our code right now. Close receive data. Close receive data is still not being used right now. So 1/5, so 2/5, so 3/5 is our problem. Why are we disabling Archeon? I have a feeling I have a feeling this is erroneous. Let's see. I think we should not disable arc there. So I have a feeling that's the problem. So let's run this. Let's start debugging. Let's see what happens now. Cool. Wait. Are you stuck somewhere? What is up? Run. Start debugging. Please take me to where I need to be. Okay, cool. Go here. Run. Start debugging. Please. Okay, cool. Perfect. Run. Stop. Run. Stop. Okay, cool. Run it now. Run the code. Stop it now. Let us observe what happened. And basically, you want to see the last one. So this is an arc. And then an arc. But why do we get an arc now? Yeah, still wrong. Okay. So the code that I just disabled, that I just disabled, so let's stop here. Manage knocking. This. I want to try when this is 2. Okay. So, from blocking I squared C, when you're using blocking I squared C, on the second last bit of
This was the wrong code to mess with because device is in master mode and it's receiving.
Just give me.
I'm just gonna look at some code to see how it's running itself. So I'm gonna look at some reference code here. My issue is I think I'm doing my arc enable and disable at the wrong time, which is causing my so I have a feeling I'm either not disabling the arc when I should, and then that is causing that last knock because and when you're doing blocking I squared C, um, I'll show you. When you're doing blocking I squared C, whenever you do get to the second last, but this is an RX thing, but we'll look at it just now. Whenever you get to the second last byte, you need to disable arcing. But let's look at it. I want to look at the drivers. So the reason I kept jumping between IDEs is because the STM IDE is where I have some old drivers that I have confirmed over and over again that are working, and most of these drivers are blocking drivers. And when I moved to around the time when I started wanting to write my own make file and my own startup file, I moved to Visual Code and stopped using Eclipse because Eclipse can be heavy, but there's nothing wrong with using Eclipse. Anyway, so most of my reference code is in Eclipse right now. I want to look at my blocking I2C driver just because I realize that's where most of the this is my implementation really, the one I'm using. So I want to see init is doing okay. So what I want to see is send data. We do a start condition and then we confirm a start generation, send the slave address, confirm the slave address, while length is 0, while length is above 0, we just keep checking TXC and keep putting in. Read SR1, read SR2. And I keep referring to this code because this code works. If we look at it, it does send and receive properly. What function is this? That's receive data. So RX data is okay. While length is equals to 0, you see here, while length is equals to 0,
is above zero. So when it's not zero, close comps.
So I think it's maybe also the way I'm doing BTF stuff.
Mm,
Okay. So just a moment. So let me look at this. So that's the event, and that's a buffer. So the buffer event and line event. Okay, good. So handle SB event, that's being handled. Okay. Handle their addressing event, that's being handled. Okay. Yes. Clear DDR flag. Handle BTF flag. So BTF I'm handling here. That's the other part we need to see. I never do handle BTF. Mm, mm, mm. I never do handle BTF. That's the problem. See here, it should say handle BTF.
when should we handle BTF? Whenever we're closing the transmission. Why do we never get to handle BTF? Because we're checking for BTF and an event. And should we be checking for that? Okay, I'm gonna try this and see if that
Save.
run start debugging. If that fixes it, I am going to be very confused because that will mean yeah, that doesn't fix anything. TXE arcs failure. Okay. Close.
Yeah, we do address one, so this is one. Why is the BDF flag not firing? Okay, so my issue is that my BTF byte transfer finished. So let's look at my. Let us look here. Cool. Let's jump into the reference manual and see if there's anyone chatting to me. No one's leaving messages. I'm alone. Cool. No worries. Master mode. Debuff N. That's it. So, no. Start debug. I wanna look at. Me? Is that where you are? Is that where you start? Wait. No. Start debug. No. Start debugging. Yes, I think I've narrowed down my issue. Okay, cool. I wanna go look at I squared C1. Okay, CR1, SR1. Where is BTF? BTF is going to be in as CR2, CR1. Just a moment. Squared C, CR1, BTF. BTF is 0, no. CR2, BTF is gonna be the first one, no? CR2, 0 to 5 frequency. Okay, then it's going to be SR1, SR2. But this is just a flag. SR1. SR1 has a BTF here. Okay, so I need to enable, let's see, where do we enable BTF? Control 2 maybe, buff N. Buffer interrupt enable, buff N, bit 10 of CR2. Why? How come? Okay, I'm noticing an issue. Run. Start debugging. So we should no here. Run to there. Okay. I think I'm using I2C one, yeah, I squared C1. Perfect. I squared C1 here. Buffer event is okay, cool. So let's drop into here. No. Stop. Run. Start debugging. This might be just a timing thing. Stop. Run. Start debugging. look at I squared C2, I squared C1. Okay. So, okay, cool. So now here we want to step into P clock control enable. That's okay. That's not gonna affect us here. We won't see anything. Cool. Yeah, that's fine. CR2 peripheral clock speed frequency should be set up to this. Cool, that's fine. Our address even slave mode. Cool. Or R2 should be set. No. Okay, cool. R1 should be set. Step over. Okay, cool, that's fine. CCR, this should be in speed, and it's gonna be in, I think, CCR. There's a CCR register. Yep. See, CCR affected. Cool. And with T-Rise. T-Rise should also be set. T-Rise is set. Okay. Peripheral control. I see the problem. So mm. 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 Okay, I wanna go to return. Okay. Drop into. I'm doing a couple of things wrong here. So first of all, my busy state. Think about it. So I start by collecting this. I set it to that. And then, but it's going to be neither this or neither that. And then I return this, which ideally should be, which ideally I should, what am I trying to say here? Ideally, I should set it and then return it. and I'm not doing anything here. Here I'm just doing a comparison. If you don't notice, so what I want to do is, I wonder if this is affecting my code, because I am using those. I am using those. I mean, this is 0. What if I do a return pi to c handle dot rx rx dxrx? What happens if I do that? Run. Start debug. Exit. And I just open it. And I just open it. I never handle the BTF. I never get into a place of handling the BTF flag. For some reason, the BTF flag never fires, and because the BTF flag never fires, I never get to actually this is buffer. Run. I can go back to how that was, but that still works. But I can go back to how it was. But that's so BTF. Where are we? So we enable the buffer interrupt, but we never get a buffer interrupt. We enable the buffer interrupt, but we never get. Uh, we enable the buffer interrupt, but we never get. Um, but we never get. It never gets fired. Mm, mm, mm. That interrupt never gets fired, and that's a problem. Why don't we ever end up in here? Okay. What is that word? Event. CR2. So that is
Event.
the event.
Okay, cool. So this isn't possibly what we wanted, but we have an idea of what is wrong.
So the BTF flag is never fired, and because the BTF flag is never fired, I wonder if it's because we're not delaying enough, or if it's because why would the BTF flag be fired? Buffer is enabled, error is enabled. Before sending of the data. I mean,
Could be a timing issue, and we are generating because if we so I want to enable all my interrupt and then do the start condition because it's all nothing is blocking. So the interrupts need to be ready already. Okay. We could be just missing an interrupt because we are firing. We have it enabled at the wrong time. Okay, cool. So it's not that. The address. The address. Then the with the address. Okay, cool. I'm gonna stop here. It's been 1.5 hours. I've been staring at the same lines of code. But we know now what is happening. We know now why it's breaking. I can, I basically can. There is some timing issue, most likely, which is causing my byte transfer finished interrupt not to fire, and I need to kind of dig into this. All of this code is open source, so if one does want, you can dig into it and open a pull request or whatever, and see if it does fix it. Mm, It seems my issue is some sort of timing issue or something like I have something happening. There should be a delay somewhere, and there isn't a delay. Um, Something of the sort. But the error here is that I think we have a shift register, we have a data register, and there's some I am mismatching their conditions so that my byte transfer finished interrupt is never fired, and that's what is causing my error at the moment. So I'm gonna pause here. I'm gonna stop, and um, I probably will come back tomorrow with a solution and do another stream tomorrow showing the solution. But I need to stop and pause and find out why this isn't working. Likely issue is there's a timing issue between when I do my TX handling and when I need to handle my BTF interrupt.
Thank you so much for coming on the stream today. It's been a good one. This has been good, I think. Although I think I've been showing basically how you break down a problem. I haven't shown you how to fix it yet, but I've shown you how I break down a problem and start tackling it into something manageable. So now I know what is happening. My biggest issue right now is I am not getting a BTF event firing, and because I'm not getting a BTF event firing, that is causing my last byte to my slave never to be arced. So I need to make sure all my timings are right so that I can get my BTF um, interrupt firing. Amazing. Thank you so much. It's been awesome hanging out with you, and let me know what you think. Cheers. Yeah. Join our servers, join the Discord, down in the description. Find the code down in the description. Contribute. Open pull requests. Open issues if you're willing to describe them well, and let me know. Cheers. Thank you.